slides on Monday.
Yeah, okay. But it slows down glycolysis.
I think so, yeah. Okay. So acetyl-CoA carboxylase, right, which is the enzyme that cuts acetyl-CoA to malonyl-CoA, is a regulated enzyme. Right? So if we have low blood sugar, right, we do a cascade, we phosphorylate it, it becomes inactive, so we do not do fatty acid synthesis, because in general, the state of the body is not energy strong if we have low blood sugar. Insulin, however, activates citrate lyase, because in this case we do have high blood sugar, right? So we do want to be eating up energy to make fats. Right? And then citrate is a feed-forward activator of this enzyme as well. And finally, the end product is an inhibitor of the carboxylase if we have too much fatty acid. So there's quite a lot of regulation of this process, and it occurs kind of where you might expect it to, in the key step that generates the unique metabolite that's synthesized, that's only used in the synthesis. Right. The other regulation step is on the fatty acid transport. So if we're building up a lot of malonyl-CoA, and we need to so we're basically committed to fatty acid synthesis, right, because of the other hormonal controls and other activators and inhibitors, then a lot of malonyl-CoA will block the transport of fatty acyl-CoAs into the mitochondria, so that we're not doing oxidation and synthesis at the same time. So we never want to be doing, they're in separate compartments. So the way to block it is to block the transport of the necessary precursor for beta-oxidation. Right? So maybe this excess fatty acid, then, if it can't get out, would have to get put back into the bloodstream and stored in fat cells. And, so if you don't demand the use of energy by exercise and such, it's going to end up getting built up somewhere. Okay? So that's your connection between fatty acid oxidation and fatty acid synthesis. So next we'll talk a little bit about the fatty acid elongation system. So now we're making molecules that are longer than, are 18 carbons and longer. And the process of this synthesis, we're not going to go into any of the details really, but you can notice that there are elongation steps and then there are desaturation steps, desaturation, elongation, and they're kind of interspersed with each other. So the palmitate, so there has to be a movement process. There's this palmitate, which it's getting made in the cytosol, has to get moved into these other compartments so that these further reactions can occur. These two, linoleic and linolenate, get made only in plants. So the plants have these enzymes and we don't. So these are essential fatty acids for humans. Right? We have to get them in the diet, and we have to get them from eating plants. So you can't be a strict carnivore and eat only meat, because if you are, you're not going to be able to make your arachidonic acid, which we'll see in a couple slides, is a crucial signaling molecule. Right? So here is a general slide. This is not necessarily linked to a particular spot in the pathway, but how desaturation of fatty acids occurs, right? So start looking over here. So NADPH is oxidized, right? So that cytochrome B5 which has FAD bound, is reduced, right? So this is a redox transformation. And then this is reoxidized so that this is reduced, right? So that's normal iron 3 goes to iron 2. And then iron 2 is reoxidized so that this guy can be oxidized. So we have a little bit of an issue here because the way this is drawn, oxidation, oxidation. So clearly there's got to be something else going on. And what else is going on is this, right? Water getting reduced to, oxygen getting reduced to water. So the reduction of O2 from water, so the electrons that are coming from NADPH and electrons from here are both ending up on O2. So that's quite complicated in terms of how it works on the enzyme. Right? We're not really talking about those details. But what we are seeing is oxygen getting reduced to water, and we call this an oxidase enzyme because it's the class of enzymes where if molecular oxygen is an electron acceptor, but we don't get any oxygens in the product. Right? I mean, we have an oxygen here, but it's not linked to that one. Right? Instead, we're just spitting out water. So that's an oxidase. An oxygenase, as we'll see in a moment, is a type of enzyme where the O2 results in oxygen added to the substrate, as opposed to O2 where the oxygen just goes off into water. So that's a desaturation. And then this is simply a slide that shows you the introduction of successive double bonds in a particular pathway, oleic, linoleic, linolenic. These are the plant enzymes, right? They can take the C18 with one double bond and add the double bond. So basically these steps are going from here to here where you're adding multiple double bonds. For whatever reason, we don't have these enzymes. So we need to get them. We need to, not the enzymes, but we need to get the precursor fatty acids from the plants. So arachidonic acid basically looks like this. So this one's actually got 4 double bonds in it. Now, interestingly, once we have 3, we actually do have the enzyme that adds the 4th one. But here's the structure of arachidonic. You have this nomenclature with the 4 double bonds, right? And arachidonic can be processed further to generate important signaling compounds, short-range signaling compounds called eicosanoids, which include compounds such as prostaglandins and thromboxanes. These are some of the types of eicosanoids, which are short-range signaling molecules. Arachidonate gets transformed by the cyclooxygenase activity of this enzyme COX, which is a cyclooxygenase. And this is where, so you notice that we are adding oxygen, and the oxygens are appearing in the product. So this is now oxygenase, and not instead of oxidase. So you might remember the distinction between those 2 classes of enzymes, just as a matter of nomenclature and knowing a little bit about the kinds of enzymes that are out there. So here, cyclooxygenase, first it can add oxygen, right? And then it has a peroxidase activity to take this peroxide off, because the addition of oxygen results not only in this bridged peroxide, but another one here. And for whatever reason later on, this one needs to come off. So these compounds, these eicosanoids, can induce narrowing of blood vessels. I mean, they have many useful uses as well. But this is sort of a side effect of them. And so if you have patients and people with blood clotting problems or cholesterol problems and you have narrowed arteries, the reason that aspirin can work as a drug to help blood flow is that it helps to clear arteries because it cuts down the activity of this guy. Ibuprofen does the same thing by a different mechanism. But these are called non-steroidal anti-inflammatories, or NSAIDs. So that's where they act. And this is what aspirin looks like. And so the way it works is it transfers, this is acetylsalicylic acid, transfer the 2-carbon unit onto a serine of the COX enzyme, and then it's dead. Okay? These guys work by binding in the same place and sort of mimicking the substrate in some way. They don't transfer they don't do the same chemistry. But ibuprofen, you recognize these names as stuff you can buy over the counter. Right? And they're all inhibiting the COX enzyme. Okay? Now it turns out there's 2 kinds of COX enzymes. So one of them is in the gastric tract, and it regulates mucin secretion. So the problem, and that's COX1, the problem with aspirin is it hits both of these. So there's 2 isozymes. If you look carefully at this, I dare you to see the differences in structure. And you can find them. But in fact, the differences are sufficiently great. This is some kind of tribute to drug designers in the pharmaceutical industry that these compounds, including Vioxx, right, can block this one, but not this one. Or does it go the other way? Yeah, block this one, which is mediating inflammation, and is the one that you want to cut down on. So an anti-inflammatory would target this. But if you target this one too, then you end up with, you know, gastric problems. You end up with stomach acid and stuff like that. So that's why people don't like to take aspirin, even though it's beneficial. So wouldn't it be great if we had a drug that hit only number 2 and not number 1? Well, that's what Merck did. They came up with these drugs. The only problem with it is that this guy turned out to be huge cardiovascular side effects. And what was worse is Merck lied about it, in lawsuits. This guy is off the market now. As best I know, this is still on the market. But it's a whole story of drug design and pharmaceutical intrigue and enzyme chemistry. But yeah, so if you're interested, I encourage you to look into that. Okay, I'm sorry, we're going a little bit fast here. So I only expect you to know this stuff in sort of, you know, bare outline. But the last thing I want to do is just show you a couple slides on cholesterol. So all the carbons in cholesterol come from acetate. This is what cholesterol looks like. The essential unit of the synthesis is an isoprene, which looks like this. So this isoprene unit is very useful as a building block for lots of different kinds of compounds. It's also useful in commercial industries as a building block to make things like rubber. Right. So cholesterol has, I guess, 27 carbons, I think it is. In this structure, it's got these 4 fused rings and then a little piece on the side. And of course, it's built up in membranes. It has a very important function structurally in membranes, mediating membrane fluidity, getting built into LV